Everyone. Good afternoon. My name is Jayaprakash Balachandran. I lead the POC workstream in ODSA, and I'd like to talk to you about the Accelerator POC, the proof of concept that you've been working on. It falls under the ODSA track reference designs. And so before I get started, I'd like to acknowledge all the companies that have been contributing to this effort. So thank you all. So let me first start. I give you a brief introduction about what the POC is all about, why we do the POC, and then I'll tell where we are in the POC process. So Moore's law has been slowing down for quite some time, and the key solutions in the industry has been the heterogeneous computing, chiplets, and domain-specific accelerators. Right, the chiplet solutions are done by today companies that are more vertically integrated, and so this is not really a scalable path. And ODSA and OCP envisages the chip designs in future will be composed of multiple chiplet solutions from multiple companies. And how can we do this? Sourcing from chiplets from multiple companies. So this is will be very similar to what we think as a PCB design today. And in order to achieve that goal, we need a development platform where we can bring in chiplets from different companies, put together, evaluate, and test. And that's what is missing today, a development platform where we can bring these accelerators or chiplets from several companies and test it. And POC is one such attempt to do that. Is essentially a development platform for accelerators and chiplets. Uh, um, so the POC objectives are, it's a yearly software development vehicle. So typically the chiplet-based chip designs can take a while to develop the hardware and the packages and together. This is an early prototyping platform where you can develop software, evaluate architectures, and you can also use it for chiplet bring up and test. So those are the key objectives of the POC platform. And so what does the POC platform look like? So essentially the heart of this platform is what is called a pitchlet. So you see here in this block diagram, there are three pitchlets. Pitchlets are modules which implements the functionality of the accelerators or chiplet functions. See, the pitchlets are interconnected in a mesh fashion using high-speed interconnects. So these interconnects are protocol agnostic, can support up to 112 gigabits of data rates. And is not, I mean, this interconnects can implement variety of protocols, being protocol agnostic, such as PCIe or Ethernet, or even source synchronous protocols, die-to-die interconnects, such as a bunch of wires. And and also you can see here, each of these pitchlets has got some special functions. So the pitchlet A is, will be connected to a host link with a by16 PCI Express link. And then the pitchlet B has got, and A will have a Ethernet functions with up to 200 gig with the QSFP interconnect. And pitchlet C is will have a M.2 interface. So the M.2 interface, you can connect an NVMe SSD or an accelerator, M.2 accelerator. So all this actually are managed. All these pitchlets can be managed using a management link consisting of a simple I2C or a SPI bus that goes across all the pitchlets. So the other interesting thing about the pitchlet design is actually the pitchlet design is specified such that if you design a pitchlet for one slot, it can be inserted in any of the slots here. So if you have a design that actually goes in a pitchlet A slot, it can be also be used in pitchlet B and C. So this gives the maximum flexibility for composing your architecture based on pitchlets. So you can try in different slots and evaluate different architectures. In addition, it has a number of debug features, USB, UART, and other JTAG and other debug features. And JTAG functions can be particularly useful for developing a chiplet with a lot of test functionality. That's something JTAG daisy chain is available within this architecture. So the platform itself has the power and cooling mechanisms. So it's all in all self-contained. So far we talked about what an architecture, what it is, right? So essentially the heart of this architecture is essentially the Pchiplets, which actually houses this implement chiplet or accelerator functionality. So going forward, so this is what an accelerator platform looks like. This is actually what you see, a prototype that we have been developing. And this is how it looks like. You have a base board, the base board, what we call as a Mara base board. It implements a full height, full length PCIe card form factor. And then you can see three slots here with the connectors, and those are the pitchlet slots. Pitchlet slots, and think of that as a PCB modules which implements the accelerator functionality. And then you can also see this M.2 slots on the top, and then there are fans, the cooling fans here. So if you design a pitchlet, the power and thermal are all already taken care. And so for the host connectivity, we use a PCI Gen 4 cable from 3M that connects the host. So this gives a maximum flexibility to operate as a tabletop platform. And optionally, you can also able to insert it on a server if you have a large server that it can house this card. Otherwise, you have flexibility to connect to using a cable through a 3M PCI Gen 4 cable. I'll show how we overcome the signal integrity later on about with this such a large card form factor with the PCI cables. So turning the attention on what the pitchlet is. So so the pitchlet is, so what we have is a chiplet. The chiplet is something very difficult to handle. It can be handled only within the package. But in order to interoperate test with the different components, what we do is we package the chiplet and then put it in, and then it becomes a package pitchlet. The package pitchlet will go into a module, what we call as a pitchlet. That something can be used flexibly in the platform. So as a roadmap, what we'll start with the existing technology, we're using the commercially available self-accelerator chips as a starting point for a chiplet. And over time, when the design matures and software is developed, we'll migrate to a die-to-die interface using the same software architecture. And only the interface part it varies, which with the die-to-die that gives a very high bandwidth. And otherwise, the functionality-wise remain the same. It just from PCB, we move into a package form factor. So, and the POC platform itself has designed very mechanically robust. And you can see here, there's especially when you're doing a development platform, we may want to use a temperature forcing system, or you may need change the designs in and out. So it needs to be mechanically robust. So we have the stiffener rings in place that gives a stability to the platform. And also all this entire platform is actually put in acrylic plates to enhance the further stability on the platform. So all in all, it becomes very easy to use if you're evaluating accelerator or chiplet functions. And the POC platform is also very thermally robust. A lot of work has been gone into this thermal simulation and validation. And what you can see here is a fan 50% duty cycle. The temperature, die temperature is met across different components that we envisage on this platform. And the POC platform also implements a very good, has a very good signal integrity. And the signal integrity simulation so far indicates that we can reach 112 gigabits based on insertion, return loss, and crosstalk. And so the first set of pitchlets is what you see here in this picture, the Broadcom NIC and Lattice FPGA pitchlet for management and security, and the NXP multi-core ARM pitchlet. So these designs are done in the lab. It's right now being tested. So last time when we presented similar update, those were in concept, and today these are in the lab now and being brought up. So, so what we plan to do with all this pitchlet concept and with these pitchlets is actually demonstrate a storage accelerator application where the storage from x86 server is offloaded to the NXP CPU, multi-core ARM CPU via a Broadcom NIC. So the lattice FPGA Pchiplets will actually will orchestrate and manage this platform. And the interesting thing about this is actually that this storage is virtualized such that the storage can come from a remote platform or it can come from a local platform. All this handled but within this NXP within the platform, and so it makes it very good, interesting case for a hyperconverged node. And so this is all composed within the Mara baseboard architecture. So for anyone who wants to develop an application on top of this, so what is a plan to make it available via a cloud? This whole platform, the Mara baseboard and the accelerator, will be hosted in Supermicro Labs. And what you see here is an x86 server with the cables attached to it using a PCI Gen 4 retimer and attached to the Mara baseboard cluster. So this way you will be able to develop an application, your storage or other type of application using this cluster. To start with, we plan to do 2 servers over time. This can be increased, and this will be available for anyone who wants to develop an application. So we'll plan to have a workshop to demonstrate this capability. So in terms of POC schedule, right now we have the boards in the lab is being brought up, and the software development will. We have an architecture team has put together an architecture for software, and to demonstrate a storage use case, and we plan to demonstrate somewhere around Q1 next year. So some of the future possibilities, what can you do with this platform? Right now we have a platform with Accelerator development. So some of the possibilities are the highly secure distributed storage network, computer development of computational storage algorithms, video analysis, and AI engines. These are some of the things we have been thinking through. And if you have any ideas, please contact one of us. We would love to hear your thoughts. So in summary, and so what we put together a POC platform, the proof of concept for Accelerator development is very flexible. It's useful for evaluate system architectures. It's an example of great community effort within the OCP. Multiple companies came together to design this POC platform. The first application we plan to demonstrate will be a storage accelerator. And this is something would be available to anyone who wants to develop the help with this or develop this application via a cloud-based system. And so we encourage you to join this POC workstream, and we need looking for more developers, particularly for software, to take further the storage accelerator use case. And we're also looking for other Pchiplets development, such as FPA, more data path intensive Pchiplets, and other applications such as AI inference and video analysis on this particular platform. And also need help with the future platform definition as well. So if you're interested, please come and talk to us. Thank you.
Hey, JP, thank you. Hey, JP and Mike, what we'll do is, if you wouldn't mind staying online, we'll club your question session with Arthur's at the end, if we have some time at the end.
Sure, absolutely.